What do beekeepers and hardware manufacturers have in common? The problem of counting things. On today's show, my guest has solved that problem with a microcontroller and some AI. Let's get personal computing with Shawn. Hey, Shawn, how's it going? Welcome to Microsoft Reactor.
Oh, thank you, Jim.
Yeah, really excited to virtually have you here. Yeah, you're the first guest on my show who's been joining us from somewhere else. So, whereabouts in the world are you?
Well, I'm in my secret laboratory in an undisclosed location. No, actually, I'm joking. I'm just outside of Boulder, Colorado.
Awesome. Well, glad to have you here. And I hear you've got something very cool. Because I'm a homeowner, I go to IKEA, I buy furniture. It's kind of one of the curses of being a homeowner. And they always have those little packets with just the right number of screws and bits and pieces in them. And I know they have machines that count them all out, but you need kind of quality control. And I know there's AI to do this, and AI for this normally runs on really big, powerful machines. But I've heard that you've managed to build something that can count screws and runs on a teeny tiny microcontroller that we could potentially power off a battery. Which, if it's true, it's absolutely bananas. So, is this true? Is this what you've built?
Yeah, absolutely. So I've got a little demo right here built on the OpenMV. So this is a ARM Cortex, I believe that's like an M7. So it's a pretty powerful microcontroller, but it's still a microcontroller nonetheless. And this is an OpenMV, so it's got an integrated camera in it. And that's taking a bunch of images. I believe I'm up to like 12 frames per second. And the model that's running on here is known as FOMO, and this is something that Edge Impulse developed. The joke is fear of missing out, but really it stands for faster objects, more objects. And it's a trick. It's a really slick way to use image classification and then divide that into grids and then figure out which each of those grid points are. So you can sort of do basic object detection in a really slimmed down way that will run on these resource constrained devices like microcontrollers.
That's really, really cool. Can I see it in action? I really want to see this in action because this is very exciting stuff to me.
Yeah, absolutely. So I believe I've got my screen up. Here we go.
Mm-hmm.
And this is the OpenMV IDE. And you can see what the camera sees.
Mm-hmm.
And let's say you have a conveyor belt, right? Kind of the conveyor belt's coming through. You can see my cables right here. And it starts to pick up these screws and washers. So now we can start to count these. And you can see the screws are in green. They've got green little circles over them. And the washers are yellow. And it works really well for these conveyor type situations where I don't have much here. And then something comes along and now I can start to count them. Now, if I get farther away, you can see it starts messing up, or if I get too close, it thinks some of them are two. So there's a particular distance where it works well. And that's how we're starting to count small things on conveyor belts. Great for assembly, for factory, but also good for, think about a escalator and you want a people count or people coming into your store, you can do that as well.
That is just unbelievable. The fact you're running that on such a small constrained device, and that is a live feed coming from a camera. So I've actually got one of the devices here myself. I managed to pick one up. So I've got one of these myself. I'm looking at it right now. So this is the OpenMV board. It's got the camera on it is tiny. I mean, this is not a big, powerful camera. We're not talking like a big, a webcam type thing. This is a small camera. And the board on it says not very powerful, and this is doing all the logic on the OpenMV board, and then it's connected to the ESP32 just to provide internet connectivity essentially. So we've got a teeny tiny chip on here that is not only grabbing an image from a camera, processing that image, and then it's running an AI model against that image. And then from what you're showing, literally in real time, and that was 12 frames a second it was running through? 12 times a second. It is able to recognize and count a screw. Now this is not a big GPU, this is not running the cloud, this is a teeny tiny piece of hardware. It's just mind-blowing. It's absolutely mind-blowing what this is doing. So let's dig into some more. How does this model work? How do you get it running on such a small constrained device?
Yeah, so keep in mind, use the term constrained here. So we have to remember that this is what we're calling constrained object detection. If you're used to doing anything with object detection, you're probably used to seeing that nice bounding box over the object, like, oh, here is my face, and it's got the square, and if I move in and out, the square kind of follows and zooms with me. And if you notice that they just have circles over the center of where those objects are,
Yeah.
and that's because of how we're doing this constrained object detection. It's not full object detection. It's constrained. So you're not going to get the bounding box. You're not going to know where is, the extents of your object. It just kind of says, I think there is a screw over here in the image somewhere. If any of you have played with image classification and you've done any sort of transfer learning, you've probably come across this very popular model known as MobileNet, specifically MobileNet v2. There's a version of this called MobileNet v2 SSD for single shot detection or single shot detector. That's for doing full object detection. I'm just talking about the classic MobileNet, where it just does image classification, and it's trying to look at this image, and this is just a fake image that I'm feeding in through this very fake actual classifier that's just a block diagram. And this is my dog, right? We want to say, is this an image of a dog? So we might feed this through a trained version of MobileNet, and it spits out some sort of prediction, like, yes, there is a dog in this image. And it won't tell you where the dog is. It's just, yes, that is dog.
It's a dog versus cat and hot dog, no hot dog, to quote Silicon Valley. It's that kind of, it's just one or the other, or it's this or not this.
Well, not necessarily. MobileNet can actually be trained for a variety of classes. So you can train MobileNet on something like ImageNet, which is this huge database of images. And each of these images is classified. It's got a label with it. So it's not just dog or not dog. You can train it to be dog or not dog, but it's also like dog, cat, horse, plane, car, truck. And so it's got, I believe you can get up to you can go anywhere between like 10 and 1,000 classes, depending on how you subdivide your different labels. So a MobileNet that's been trained on something like ImageNet can be very powerful for classifying across a variety of different labels. And that's usually where you see something like MobileNet being used. It's not just dog or not dog, it's dog versus cat versus this other thing, or I don't know what it is, just some sort of background image. So that's where we get into MobileNet. We start with this idea of MobileNet, and it's built on these residual blocks, which I won't get into because I don't quite remember how they work. I did look into it, but I don't quite remember the exact math behind the residual blocks. But the idea is it's built on these 17 residual blocks as the image goes through a series of transforms, generally like convolution, and it's trying to pick out different features. It gets higher and higher order features from this. So maybe it finds a nose and eyes and ears, and it goes, oh, in this particular configuration, I think this is a cat, or I think this is a dog. So what we do for FOMO is we actually take MobileNet and we slice it. We slice after that third residual block, and we create essentially a classifier for each of these cells, these feature maps that are coming out of that third residual block. And because we are using these residual blocks, that 240 by 240 image, it could be 96 by 96, take your input image of choice, that gets divided down 8 times. And so you end up with these 30 by 30 cells, assuming a 240 by 240 input. And each pixel, for lack of a better term, each feature in those feature maps can be classified individually. So we're basically doing image segmentation now based on these feature maps. And then to classify those individual cells, we send each of those through these fully connected layers. That's just a basic dense neural network, or fancy name for a dense neural network. We do that by doing 2D convolution with a 1x1 kernel, which gives us the same math as fully connected or a dense neural network. And then so we end up with something that looks like segmentation of these feature maps. And then I'm going to go forward here. And then so this is where you have this 8 by 8 pixels. This gets compressed down to this one single feature cell, and then we classify that individual cell. So in this case, maybe I've trained this to look for background, ball, dog, toy. And now we start to get an idea of which cell or which grouping of 8 by 8 pixels contains one of those classes. And then so each of those cells is classified. So background, ball, dog, toy. And then it can identify where those are. Does that give you an idea of what's going on in FOMO?
So essentially, you've got this idea of like a classifier that says this image is hot dog, not hot dog, dog, cat, fish, hippo, whatever it is. And you're taking an image, you're breaking that image down into very small chunks, and just almost like, and I apologize, this is a horrible oversimplification, but it's almost like you're running that classifier on each of those individual cells, so each of those small blocks on the screen.
Yes,
And then because you're saying,
exactly. Yeah, we're classifying each cell.
yeah, so if you think about a classifier, you could have a picture of a dog, and the dog could be in the top left, and goes, yeah, it's a dog. Or the dog could be in the bottom right. Yeah, it's a dog. You don't know where the dog is. It's just there as a dog in the picture. So if you shrink that down to the smaller scale, if you're running this classifier on a teeny tiny little portion of the image, if it goes, yeah, that's a dog, you don't know where in that portion of the image the dog is. It's just there's a dog there. So it's almost like you're saying, yeah, it's kind of roughly about here, hence why you have that circle. So you don't have a bounding box. You're not saying this is the exact location of the dog. You're just saying, I've classified this part of the image. There is a dog somewhere in here. Therefore, I'm going to stick my circle here to say it's roughly there.
Yep, exactly. And we do some techniques where if two circles appear next to each other on like adjacent cells, we actually just get rid of whichever circle has the lower score. So you end up with just one circle, which creates some limitations with FOMO in that if you have a bunch of objects, say cars or bees in this case, and I'll get to this story in a second, that are next to each other, you don't count them. You end up just not counting one of those. So that creates some limitations with how you need to feed it images to train, and understanding that you really shouldn't count things that are going to be next to each other. You have to assume that there's going to be a cell in between them if you want to do more accurate counting. So knowing those limitations, like this is one of those things that you give up having a full bounding box, but now we can run it on a microcontroller for less money, less power, and so forth.
Tell me about the bees.
Bees. So bees, the machine learning engineer who developed FOMO for Edge Impulse, his name is Matt Kelsey, a super cool guy. And he was working on this project where he keeps bees, right? He lives in Australia. He's got, some land, and he's like, I want to make some beehives, and I want to make some honey, and bees are great. Let's keep some bees. So he made this beehive, and he wanted to count the number of bees, or get a general estimate of how big his hive was based on the number of bees coming in and out. Matt Kelsey's approach was I'm going to stick a camera on the side of my beehive and count the number of bees going in and out of my hive every day. And to do this, you need some machine learning. And so object counting was generally part of object detection, where I detected the object and then I can count the number of times I see that object in the image. And he's, I don't want to run this on an NVIDIA Jetson, right? I can't run these big heavyweight models like MobileNet SSD, YOLO V5. And it's funny that I say that these are big heavyweight models, because in the scheme of big ML where people are working, these are like really lightweight models. But when we start talking microcontrollers, these are considered heavyweight. So we're talking, very low power devices that can't run some of these larger models. So even MobileNet SSD was too much for this. And he's like, I don't need bounding box information. And then if you notice, the camera is actually mounted to the side. He's not straight at where the bees come in and out. So he doesn't care that bees are, in, larger in frame or smaller in frame. He's on the side. Bees coming in and out are generally on a plane that's perpendicular to where my camera is shooting. So all the bees are about the same size, which means that if you construct your image, your resolution the right way, you can pretty much assure that a bee is going to take up one of those 8x8 pixels. And you can see that's exactly what's going on here. The bees are about the same size, which is perfect for FOMO. So shooting it at an angle like this, so now I can count them, not worry that they might be too close or too far from the camera. The other thing is the background is pretty much static, which means I just need to worry about differences. So I can train with like one background, and now I can just pick out the bees, which are different from the background. This is a perfect use case for FOMO. So he mounted this, and he was able to plot over time. He could see when the bees would leave during the day, come back during the day. He could get a general estimate of the number of bees over time as like the year went on. He could watch the seasons, which is cool. You do see it missing a couple of bees right in this left-hand spot. I'm gonna put my mouse over here. Right over here, you see it's missing a couple of bees. Either that was a false negative where it's not seeing it, or like I mentioned, the two cells got merged into one. So maybe this cell got merged into this cell. There's two or more adjacent cells that are the same class, it will drop the lowest ones. And so you just end up with the highest one. So there are some limitations, but in this case, he just wants to monitor the overall health of the beehive. He doesn't need to know exactly that 135 bees came in today, right? He doesn't care about that. He's just like, I want to watch overall health and get relative estimates over time. So once again, that's a better use case for FOMO than saying I need to know exactly 200 people came into my store today. So keep that in mind. Now, there are ways you can get more accurate if you can assure that certain people, aren't next to each other, or what is it, occlusion, where they're blocking each other, where you're not going to get these false negatives. That helps a lot too. So things to keep in mind when you're doing this.
So this is, you say, it's kind of a perfect example, because you've got the static background. The background's really, it's only going to change in terms of light. So, you could be capture data in the morning, middle of the day, afternoon, evening, as the kind of light levels change. But because things are the same size, we're always, that the bounding box you need when you divide your image up, what the size that is, because that needs to be the size of the B. So it's kind of a perfect case. And I guess going back to your original example with the conveyor belt, same kind of thing. You'd have a camera at a fixed point in a conveyor belt. Screws are going to be a certain size, aren't they? So it's kind of the same kind of idea.
Yes,
that's the same size. You can train the model based off just my conveyor belt. Screws are coming in. They're all going to be the same size. Yes, some are going to be up top to bottom, some are left to right. I can train it on all different orientations of screws, but because of that consistency, I know that if I divide my image into the 16 cells, or how much you divide it by, one of those is the right size for a screw, so it'll work.
Yes, yeah, exactly.
This is really cool. I absolutely love this stuff. This is so cool. And the fact you say you can run this on these tiny constrained devices. I mean, I've joked about building a bear detector for my back garden, because I live in the Pacific Northwest and I get bears coming in. So if someone wanted to get started with this, how can they get started? Do we have, is all this open source? Is it expensive to train these models?
No, not at all. This is just a quick page I put together that, getting started with FOMO, and that we've got a couple of example projects to walk you through. There's a tutorial here for Edge Impulse that shows you how to work with FOMO and train a model for using, image data. And then we've got the actual washers and screws. That was the model that I was running. This is the exact model. So if I click on this is a public project. You go here, and sure enough, here's the public project. You can clone it into your Edge Impulse account. And then down here, you can go to deployment. And I can't deploy it right now because this is the public view. But as soon as you clone it, I cloned it to Arduino. Oh, no, excuse me. I cloned it to OpenMV down here. So it's an OpenMV library, but you can also get it in a variety of libraries from Edge Impulse. We've got the C++. As long as you have a C++ compiler and enough RAM and flash on your device, this will absolutely run. And a number of other things that have, acceleration in them. So we've got like BrainChip. We were talking about NVIDIA earlier. Yep, absolutely. You can run it as a Tensor RT, and then it just, you just spit out a library for yourself. So we've got a few of those examples if you want to get started. Most of these are more demonstration, so I wouldn't expect the models to work at that 99.999% level, but it's enough to get you started and start playing with FOMO to understand how it works and start understanding some of the limitations behind it. So you can start thinking about, okay, how can I structure capturing data as well as performing inference in a real life situation, and what more data would I need to get in order to make this more robust for like industrial standards. So that's where I recommend going for that. So this is the screw washer Azure IoT demo, and that was the model that I just showed you from the screws and washers. By the way, if you want to see, I can go to data acquisition here, and I can click on, say, screw, and you can actually see, right, here's my conveyor belt that they were collecting this original data on. And so you got screws and washers, and these are manually labeled. So somebody went through and manually labeled, drew a little bounding box over each one, and that's what feeds into the FOMO classifier or the FOMO training in order to get that model out to perform inference. But this is a quick demo that I put together. So we've got this is the OpenMV, so it's all written in MicroPython. So you've got the actual code that I was showing earlier in OpenMV. And then there's the Arduino side, which we haven't even started to talk about yet. This is based on the Azure IoT Central demo for Arduino. So I just took this and modified it a bit. So if we go into the INO file, you can see this. I modified it a little bit. So all I'm doing is over serial. I'm capturing from OpenMV, or from that OpenMV camera. It's just, that one wire basically plus ground was just giving me, hey, I see this many objects every second or so. I see this many objects. I see this many screws. I see this many washers. And from here, if I go into Azure, I can see number of screws over time. It's actually giving me number of washers, number of screws. And then you can see this. So this is going to take a second to update because it takes a bit to get across there. And I'm going to bring up here we go. So we can see what's going on. So I can show you this end to end. You can see the washers and screws being counted here. I'm going to make sure I have that right. The correct position, because apparently it gives me some false positives here. It confuses screws and washers a little bit at that angle. So I'm going to go right over top of it, get a little closer to try to get that conveyor belt look. Here we go. So it's counting screws and washers here. And then if I go to Arduino, you can see it's receiving these messages. And I want to say it's like maybe one a second, one every few seconds. So you can see number of screws. Let me get my mouse over here. You can see number of screws, number of washers coming by. And it should be 2 and 2. I'm doing my best to hold my hand steady over this camera. And then I'm going to go back into Azure. And sure enough, you can see these start coming in now that I'm holding the camera over it. And all that information is being piped out. So the OpenMV is doing the actual object detection with FOMO. That's just sending some numbers to the ESP32. And all the ESP32 is doing is talking to Azure over the cloud. So it's just connecting to my Wi-Fi and just pumping these numbers to Azure and say, hey, update these values on Azure. So you can see 2 screws, and it should be 2 washers coming in. Somewhere it counted 3 because it, false positive, and I'm not holding the camera steady. But I hope that gives you an idea of how we're able to use this idea of object counting, even in a constrained manner, using small microcontrollers in this case, and then piping that data over to some sort of IoT collection bin. And then you can do something with this data. Maybe you generate reports, people who used our parking lot, number of customers in stores, number of screws produced on our conveyor belt or coming through the conveyor belt. I hope this helps you get an idea of how you can start constructing those pieces for using machine learning, specifically object detection and object counting in industry type of settings.
Yeah, this is awesome. Yeah, you can count the bees and you have this dashboard running in your house. This is the number of bees going in and out. It's going to get that lovely view on it. This is great. Thank you so much for showing this off. I must admit, I do love the stuff Edge Impulse are doing. And this is all free, isn't it? You can use FOMO, get started with FOMO for free.
Yep, absolutely. We have a free developer account. So if you just create an account on Edge Impulse, there's a number of tutorials. Our documentation's really good. I have a course on Coursera. If you're new to the idea of using AI, especially like AI on microcontrollers, where I walk you through a number of instances of doing both, let's do the simple magic wand gesture, let's do keyword spotting, and we get into the follow-on course on Coursera. We get into doing image classification and a little bit of object detection. I haven't updated because I released that course before FOMO was released, and so I need to update it with FOMO because it's super cool how this works, and teaching people about how to use FOMO and the limitations of it.
Awesome. So anyone watching this, if you're suffering from FOMO, get onto Edge Impulse and actually get the model created, get your data up in Azure. This is so cool. Thank you so much for taking time to join me. So we'll put all the links in the show notes. Everyone can come and recreate these. But thank you very much for joining me.
Yeah, thanks for having me on the show, Jim.
As cool as this project is, what's even cooler is you can recreate this at home. Check out the link below for everything you need.